everyone, in this video we will talk about asymptotes in rational functions. So we're going to be focusing on how to identify which type of asymptotes occur based on the equation, and then we're going to look at why do they occur. So first of all, what is an asymptote? It's a line that the function approaches but never actually reaches. And here's something else that's good to know. It's actually okay for the function to cross the horizontal or oblique asymptote as long as the end behavior still looks like an asymptote. And so here are some examples. This is y equals 1 over x. So you'll notice horizontal and vertical asymptotes. So the function is approaching these lines, but it's not actually reaching them. This one over here has a horizontal asymptote because it's getting closer and closer to y equals 0, but it actually crosses back and forth over it an infinite number of times. And you'll also notice over here that it has a vertical asymptote. And then this is a function with an oblique asymptote. So this is the oblique asymptote. It's a slanted line that it's approaching on both sides. And it also has two vertical asymptotes. So some of these graphs can get pretty interesting. So first, let's take a look at vertical asymptotes. So this is a vertical line that the function approaches. And we can find its equation using the 0 or the zeros of the denominator, as long as you don't get 0 over 0 when you sub those x values back into the function. Because if you have 0 over 0, then that will give you a hole rather than a vertical asymptote, and we're not really going to be talking about holes in this video. So let's look at an example. Here we have y equals 3 divided by x minus 4. So if we set the denominator equal to 0, and we solve for x, we get x equals 4. And so if we check, we sub in x equals 4, we do not get 0 over 0, so we can conclude there's a vertical asymptote at x equals 4. And so here's the graph, and you can see, yes, this is the vertical asymptote at x equals 4. Okay, so why does this occur? Why do the zeros of the denominator give us vertical asymptotes? Well, first of all, we know that there's not going to be any y values at the zeros of the denominator, because we can't divide by 0. So for example, in this function, x cannot equal 4, because that would result in dividing by 0. So it makes sense that there's no y value when x equals 4. But what causes this behavior where it ends up approaching a line like this? Well, what we can do is look at the limits. So first of all, let's look at the left side. We notice that as x approaches 4 from the left, y approaches negative infinity. So we can write this as the limit of the function f of x as x approaches 4 from the left is negative infinity. And so why is this true? Well, let's think about what happens to this function f of x if x is a little bit smaller than 4. So for example, we could sub in x equals 3.99. This makes the denominator just slightly smaller than 0. So now we have 3 divided by a negative number with a very small magnitude. So the answer is a negative number with a very large magnitude. And so you can see here we get negative 300, and if you try to number even closer to 4, then you'd get an answer that's even closer to negative infinity. And next we can look at what is the limit of f of x as x approaches 4 from the right side. Well, that equals positive infinity, as you can see over here. And so again, we could sub in a number to test this out. Let's sub in 4.01, a number that's a little bit bigger than 4. This gives us a very, very small denominator, so the answer is a very, very large positive number, which demonstrates that it's approaching positive infinity. Okay, so next let's look at horizontal asymptotes. So a horizontal asymptote is a horizontal line that the function approaches. And this occurs only when the degree of the numerator is less than or equal to the degree of the denominator. So we're going to be considering each of these two cases separately because they kind of have different rules for each of them. So first of all is when the degree of the numerator is equal to the degree of the denominator, we're going to use the ratio of the leading coefficients of the numerator and denominator. So what does this actually mean? Let's use an example. So here we have y equals 2x plus 1 divided by x. So the degree of the numerator is 1 because x to the 1 is the variable with the highest exponent. And then also the degree of the denominator is 1 because again we have x to the 1 is the highest exponent. So they both have the same degree, which means that we can use this rule about the ratio of the leading coefficients. So the leading coefficients are the coefficients in front of the variable with the highest degree. So here we have 2 to 1, which just equals 2. And so that means we can conclude that there's a horizontal asymptote at y equals 2. And you can see in the graph, yes, there is an asymptote right there. So when I first saw this, I was really confused, like, why does any of this work? It just seems like such a random rule, like, how did people come up with this? So let's break it down to see what we're actually doing. What we're really doing is looking at the end behaviors of the function. So like when x approaches positive infinity and when x approaches negative infinity, and then we're looking at does the y values of the function approach a certain number, which in this case it's approaching 2. So first of all, as x approaches positive infinity, we notice that y approaches 2. So why does this happen? Let's sub in a really big value for x into this equation over here. So if x is 1,000, we end up having 2,000 plus 1 divided by 1,000, which is just slightly bigger than 2. Because notice that this 1 over here is getting less and less important as x gets really big. And so at some point, this adding 1 is basically not important at all. The thing that really ends up affecting the answer is this 2-to-1 ratio over here. And so that's the ratio of the leading coefficients, and that's why that rule works. And so similarly, we can look as x approaches negative infinity, y approaches 2 as well. So if we sub in that x equals negative 1,000 to represent a very small number, again we're getting a number that's very close to 2, because this over here is very close to negative 2,000 divided by negative 1,000. And so those negatives are going to cancel out, and that's why we get a positive answer. And so we notice again, this plus 1 becomes less and less significant as the magnitude of x gets larger and larger. So it ends up just being the ratio of the leading coefficients, as you can see here. So now let's consider the other case for horizontal asymptotes, and this is if the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is at y equals 0. So let's work with a similar function to the previous example, but now we have x squared on the denominator. So we can see the degree of the numerator is still degree 1, and then on the denominator it's actually degree 2, because now we have variable with the exponent 2. And so since the degree of the numerator is smaller than the degree of the denominator, we know that there's a horizontal asymptote at y equals 0. And so in this graph you will see, yes, here it is. And notice it actually does cross the asymptote right here. That's okay, because we still just care about the end behaviors. The end behaviors are still approaching y equals 0. So again, let's look at why does this happen by investigating the end behaviors of the function. So as x approaches positive infinity, y approaches 0, as you can see here. So again, let's sub in a really big value for x. We'll say x is 1,000, and we sub it into this equation. What we end up with is 2001, and then this is divided by a really big number because of this squared term over here. So that will give us a very, very small number as our answer, which is essentially 0. So whenever the degree of the numerator is smaller than the degree of the denominator, we can see the denominator gets so much larger as x approaches infinity that it really doesn't matter what's in the numerator. The whole thing is just going to approach 0. And in a similar way, we can see as x approaches negative infinity, y approaches 0 as well. So if we sub in x is negative 1,000, the numerator is going to be negative 1,999. And again, the denominator is going to be a really, really large number. So when we divide those, it will give us a very small number that's close to 0. So we can conclude that whenever the denominator has a bigger degree than the numerator, we end up dividing by a number with such a large magnitude as the magnitude of x approaches infinity that y will just approach 0. And the final type of asymptote that we will discuss is oblique asymptotes. So this is a slanted line that the function approaches. So it's any type of line other than horizontal or vertical. And it occurs only when the degree of the numerator is exactly 1 greater than the degree of the denominator. So let's go through an example together and we'll see why the asymptote ends up approaching a slanted line. So here I have a function y equals x cubed divided by x squared minus 2x plus 5. And so you'll notice that the degree of the numerator is degree 3, which is exactly 1 greater than the degree 2 in the denominator. So we know that there's going to be an oblique asymptote. So what we're going to do is we're going to do division of these two polynomials. And so that will just give us a different way of writing the original function, but we're not actually changing anything. And I would like to note that even though I'm going to go through like a whole long division and then like using the division statement, that's not really the purpose of this video. I'm kind of just using the division as a tool to help explain why the oblique asymptote exists. So I'm going to go pretty quickly through the division, and so if that's something that's tripping you up, then I might make another video specifically to deal with division. So if the division in here is confusing, you might just want to kind of skip past that because it's not meant to be the focus of this video. So I've set up the long division over here. So I have x cubed, and then I've put 0 coefficients in front of these other terms because they weren't already there. And then over here I put what we're dividing by. So if we divide x cubed by x squared, then that gives us x, so we can write it up here. And then we're going to multiply all of these terms by x and subtract that all. So we have x times x squared is x cubed, negative 2x times x is negative 2x squared, and 5 times x is 5x. So if we perform the subtraction over here, the x cubed terms cancel out. Here we have 0x squared minus negative 2x squared, which gives us positive 2x squared. 0x minus positive 5x is negative 5x, and then we can bring down the 0. So now we look at how many x squareds can fit in 2x squared. Well, the answer is 2, so that goes up there. And then we're going to multiply everything here by 2 and perform subtraction again. So we have 2x squared minus 4x, and then 5 times 2 is 10, so plus 10. And when we do that subtraction, these terms cancel, so we have negative 5x plus 4x is negative x, and then we have 0 minus 10 is negative 10. And so x squared does not fit into negative x at all, so we can stop here. So this is the remainder, it's what's left over, and then this is the quotient. So now we can use the division statement to rewrite this function after doing division, so it's still the same function, it's just written differently. So according to the division statement, we have the quotient over here plus the remainder divided by the divisor. And so now the key thing to consider here is, again, we're looking at the end behaviors. So as x gets larger and larger, what happens to this part over here? Well, we just talked about with the horizontal asymptote that when the degree of the numerator is less than the degree of the denominator, the squared terms in the denominator is going to make it so large when x approaches infinity that this entire term is just going to approach 0. And the same thing would happen if x approached negative infinity. So if this whole term approaches 0, then what are we left with? Well, it's just this part over here. So that's going to be the oblique asymptote at y equals x plus 2. And so that's why the oblique asymptote is the quotient of the division. And the remainder over here doesn't matter because of how this term approaches 0. And I would also like to note that this explains why the oblique asymptote only occurs when the degree of the numerator is exactly 1 greater than the degree of the denominator. Because when we're performing the division, where this degree is 1 greater, the quotient is going to be a linear function. In other words, degree 1. Otherwise, you'd actually get something like the function approaches a quadratic function or a cubic function, etc., if the numerator is more than 1 degree greater than the denominator. And so now that I've graphed it, you can see, yes, it approaches this line of x plus 2 at both of its end behaviors. So that's all for this video. I hope this gives you a better understanding of how to find those 3 types of asymptotes and understanding why they exist. So even if you forget one of the rules, you can just kind of think about the end behaviors, you can think about what's happening as x approaches certain numbers, and then that will help to give you an idea of where the asymptotes will occur. So thank you very much for watching.